pleased to introduce the speaker for this session, Barry Bolding. Dr. Barry Bolding has over 25 years of experience in high-performance computing as a business development and product strategy leader, and is the AWS Worldwide Go-to-Market Director for High-Performance Computing Plus, including HPC, Machine Learning Framework, Quantum, Autonomous and Accelerated Computing at AWS. Dr. Bolding's career has spanned technical and business roles at a number of leading HPC companies, including Cray, SGI, and IBM, and for 10 years he served in executive roles at Cray, a world leader in on-premise HPC solutions. Over the course of his career, Dr. Bolding led teams focused on business development, product management, strategic partnership, and served as the GM for HPC Storage. He received his Ph.D. from Stanford University and has published numerous papers in the areas of computational modeling of physics and chemical systems. This diverse background gives Dr. Bolding a unique and balanced perspective on the convergence of cloud services and high-performance computing and the impact this convergence will have on the enterprise and government marketplace. It will now be our pleasure to hear from Barry Bolding.
Hello. I'm really happy to be back at Big Compute this year. It's so great to have Big Compute 22 rejoining us all from our COVID hiatus. And today I'm here to talk to you about some of the ways that HPC has been evolving and changing, the ways that HPC is converging with machine learning, with cloud, and it's changing the way that we work for HPC. First of all, HPC impacts every part of our daily life. I showed this slide a couple of years ago when I was in person right before COVID hit at Big Compute. And I used it to emphasize that HPC impacts every portion of our life, whether that's in the coffee makers that we use and the design and engineering that goes into those every morning, all the way through our financial portfolios and the risk analysis that happens with those analytic tools, through the fuel we use, whether that's electric cars, autonomous vehicles, or gasoline-powered cars, where exploration and reservoir production and productivity are important in the use of those fuels and the production of those fuels. Every part of our daily life is impacted by HPC. And every part of HPC is today changing and being impacted by new algorithms, methodologies, and new ways of accelerating workloads. And today I'd like to talk to you a little bit about that aspect of HPC. We see a convergence of several attributes for HPC, and these are the acceleration of HPC through technologies and improving integration of technologies into workloads. This can take the example of the evolution of GPUs and their use for different HPC workloads all the way through today, where we see special purpose devices, special purpose processors such as Inferentia and Trainium that AWS is developing for doing machine learning inference and training workflows. There's also acceleration through parallelism. And this was a revolution that took place in the 80s and 90s as companies like Cray Research and others were developing massively parallel infrastructure to allow for HPC to solve new and challenging problems. This acceleration through parallelism is still critically important for the convergence of HPC and the evolution of HPC. And finally, there's the acceleration through new and evolving workflows and algorithms. At times, these algorithms remain static. There are long periods of time where computational fluid dynamics algorithms may not change, may not evolve. But we've seen a revolution over the last few years that I want to talk about that's really changing and evolving workflows at a more and more rapid pace. In the area of acceleration, though, it's critically important that we take our learning and experiences from one area, segment, or vertical and into other areas, segments, and verticals. We're seeing this more and more important every day. The evolution of autonomous vehicles, where driving simulations, we're using algorithms and methodologies from gaming in order to simulate road driving. We see the use of machine learning impacting CFD and CAE algorithms. We see the use of Monte Carlo algorithms for financial services and risk, the same as we see them for climate modeling. These types of workloads can benefit from the experience that teams have in moving HPC workload learnings from one segment or vertical to another. And this is a philosophy that AWS has and that our partners largely have in trying to utilize those workloads and utilize those learnings across workloads. Acceleration also requires scale, and it's critically important that workloads today have access to large volumes of compute, whether that's to solve a very large weather simulation or to solve a large distributed problem such as analyzing proteins in a database, or doing an accelerated compute of a seismic processing workload and all the shots from that workload, and doing it in an elastic fashion that allows a compression of that workload time. All of these are examples of the way that workloads can achieve new and improved results by utilizing the scale that's available to them. And of course, cloud is critically able to provide the scale needed for these types of accelerations. Critical over the last few years has been that algorithms and workflows are advancing and accelerating at a pace that is outstripping the technologies that have been developed. About 7-8 years ago, the exascale systems that are being delivered today were just being awarded and designed. So in that time frame, the on-premise vendors were having to select their designs, select their accelerators, select their CPUs to the best of their ability, and then build those systems over many years and eventually delivering them with the exascale systems that we're beginning to see delivered in places like Oak Ridge National Laboratories with their Frontier system, Argonne National Laboratories, Lawrence Livermore. All of these laboratories will have their exascale systems, but much of the design work was done in the 2015 to 2019, 2018 timeframe. At the same time, we've seen an acceleration of evolving architectures. In 2018, there was the release of a physics-informed neural networks paper. That paper, cited here, basically has begun to revolutionize the way that, that machine learning and physics-based models are being used together to solve and accelerate engineering processes. That paper alone has over 3,000 citations already, and there are multiple articles spawned from that work. In addition, we've seen an immense growth in what are called foundational or transformer models for machine learning, with those first evolving with the seminal papers in 2018, evolving very quickly through different models, including BERT large, GPT-2, GPT-3, all the way from 65 million parameters all the way through 175 billion parameters today, and targeting 1 trillion parameters in the near future. These types of accelerations in the way that machine learning foundational models are evolving is changing the dynamic of how HPC and workloads associated with HPC can be accelerated. A prime example of this is some of the work being done around AlphaFold and OpenFold. So these folding methodologies, these machine learning, deep learning architectures, are allowing new protein structures to be predicted at a far more accurate level. And so the evolution from AlphaFold to AlphaFold 2, and then the release of different folding methodologies such as Rosetta Fold and OpenFold and FastFold, are all allowing pharmaceutical companies and researchers around the world to greatly enhance their ability to develop new treatments, new drugs, and we've seen that accelerating even with the development of COVID vaccines and the groundbreaking rapidity with which those new vaccines were developed. In addition, we're seeing methodologies such as reinforced learning. There was a seminal paper in Nature recently in 2022 regarding work done in 2021 around the tokamak reactor and the reinforced learning methodologies that were used to control the fusion reaction and basically extend the length that the fusion reaction was able to be stable. Those types of reinforced learnings are also changing the way that experimentation and HPC are interacting with one another. These algorithms and innovations, evolving faster than the underlying infrastructures can evolve, mean that you need an infrastructure that is flexible and in continuous development at all times. And AWS has an evolution of HPC that has been following a continuous innovation, continuous development cycle for the last 5 to 7 years. Starting with the release of our AWS batch and other services that allow us to scale elastically, loosely coupled workloads. And we've moved that over to tightly coupled workloads with the release of HPC 6a, the release of EFA in 2019, the release of HPC 6a in 2022. We're now able to do tightly coupled workloads as well. And then we're innovating on we have to have the flexibility to have different types of accelerators to solve these complex workflows, whether that's a GPU, whether that is our P-series or G-series GPUs based on different SKUs of NVIDIA accelerators and NVIDIA computational devices, or whether that's in-house developed and designed special purpose devices and chips such as Inferentia and Trainium that are designed to be able to solve the inference and training aspects of these workloads. This continuous innovation provides choice and flexibility to adapt to these changing algorithms that I showed on the previous slide. It's critically important, though, to also look at how these applications are being put to work. So I want to spend the rest of my talk giving you a few insights into how HPC Plus, as I call it, is being put to work, where the plus is about the use of different algorithms and methodologies such as physics-informed neural nets, machine learning, or other data analytics to help solve HPC problems. HPC Plus is accelerating nearly every aspect of HPC workloads today. Whether that is seismic workloads where computer vision is being used to analyze salt deposits or analyze the size of reservoirs that are available automatically based on data as it's coming out of the seismic processing workflow, and give early predictions as to the location of deposits, or whether it's Woodside using machine learning and data analytics and predictive modeling to do digital twins of their plants and do simulations of those plants for maintenance and other predictive workflows. These types of very complex workflows are allowing applications and users today to use HPC Plus in nearly every workload we see. AWS and its partners like Rescale are also driving this flexibility and innovation. Whether this is Boom, which uses Rescale to solve and leverage AWS technologies and to accelerate the design of their supersonic aircraft, or whether there are customers like Commonwealth Fusion that are part of this growing and evolving segment of fusion research startups that are beginning to impact this really important, critically important area of energy research. They're using multiphysics and particle simulation to be able to solve their most complex problems. And then we have the therapeutic companies, the pharmaceuticals such as Moderna, that are using a complex mix of AI/ML, machine learning, HPC, and in their drug discovery workloads. We also see that these HPC Plus workloads are accelerating the design cycles for engineering. And this is very important because companies like Delara, F1, Kiyu that's developing emission-free hydrogen cars, Rivian, Ineos, Flying Whales, Joby Aviation. These are all companies that are critically dependent on their cycle of engineering research. And they're using a wide variety of partners to help enable that, whether that's the Rescales of the world, the Altairs, the Ansys, Siemens. These types of companies, the ISVs, are innovating quickly as well to try and accommodate those changes and needs for accelerated HPC workflow. We also see an emergence in the energy space, not just for the seismic and oil exploration, but also in the renewables. And the use of HPC to both design wind farms, to do assessments of locations, to do modeling prior to deployment of wind farms, as well as the maintenance, the turbine aerodynamics, the predictions of failure that are needed as digital twins for these renewable sites is critically important. And companies like Goldwind, based out of China, use AWS every day to help solve these problems. In the more traditional numerical weather prediction, though, we also see deployments of AWS's scalable infrastructures for both traditional weather forecasting, using codes like WRF and MPAS, as well as deployments by startups that are using a mix of machine learning and HPC. Companies like Maxar that are combining weather, GIS, and analytics to give their customers solutions in a very timely manner. AWS teaming up with Silver Lining and NCAR to do climate simulations going out to 2070. Weather News in Japan that is doing 10-minute rain forecasts that are very localized to be able to give their customers information on whether at the street corner level they will have a rain impacting their events. And then companies like DTN that are using weather forecasting to aid with agricultural analytics and risk modeling, or energy, using HPC 6A solutions on AWS. And finally, one of the final examples I wanted to mention was in the area of predictive modeling for digital twins. We're working with companies like Siemens and MHP to combine Bayesian methods along with computational fluid dynamics, physics-based models, machine learning, to predict failures, to predict pipe corrosion, to be able to diagnose when power plants are going to be seeing an increase in failures, or leveraging them for different models to predict performance and degradation of electric vehicle batteries. These are all work cases that need this combination, this complex workflow, and they can't get to a solution with just a single narrow focus on HPC as computational modeling or computational fluid dynamics. And finally, as I mentioned earlier, this seminal article in Physics Informed Neural Nets allows car companies or aerospace companies or space companies to do predictive designs and very fast iteration on designs. They can train models to highly accurate experimental data or to highly accurate computational models of turbulent flow. Then they can do changes in the design of the bumper or the wingtips, and then they can do an inference on the trained model that they've created. They can get a quick answer as to the reaction to the design change on the computational fluid dynamics, which then allows them to go through thousands of different design iterations in a matter of hours, then come back and do full computational fluid dynamics or even experimentation on a much smaller subset. This acceleration of the design cycle is critically important for many industries today. And finally, it wouldn't all be possible unless we had ways to share data. And at AWS, we have an open data initiative, one of which I'm particularly fond of, which is the Amazon Sustainability Data Initiative. This is where we bring together the data to allow the customers that are doing these complex workflows to be able to utilize the data and innovate on top of the data, whether that's fighting climate change with Digital Earth Africa, or creating solar forecasts in Australia, such as the company Solcast is doing, or whether this is optimizing freight shipping, such as Nautic AI does, a Finland-based company that helps to optimize real-time fleet monitoring and control. These types of collaborations and the Q-Hub that sits on top of ASDI that allows earth science collaboration on large shared data sets are critical to evolving quickly on the algorithms, helping these small startups or these scientific researchers to test and innovate as quickly as possible with as little cost. So hopefully I've given you a bit of an example today of the ways that HPC is evolving and the way that acceleration of HPC depends heavily on three factors: on the technology that is being used and the flexibility of that technology, the parallelism of the algorithms and the need to drive a parallel infrastructure, and then the algorithmic changes and how they map to both the infrastructure and the parallelism. AWS is uniquely positioned to provide the flexible, scalable infrastructure needed for advanced computing, HPC plus as I call it. Thank you for the time today on Big Compute 22, and I look forward to being in person for Big Compute 23. Thank you very much.